Warm evening to everybody. Our speaker today is Dr. Sanjukta Roy. She is a researcher in atomic physics with a research interest in ultracold atoms and quantum degenerate gases, with particular interest in few body physics with ultracold atoms and, as she mentioned right now, Anderson localization of matter waves in disordered potentials and quantum simulations using ultracold atoms. She is a senior researcher at the Raman Research Institute, Bangalore, and she did her PhD from Tata Institute of Fundamental Research, Mumbai, under Krishnan, where she built up an experiment to realize all-optical Bose-Einstein condensate in optical traps and 1D optical lattices. The above said experiment successfully realized the first BEC in India in all optical dipole trap and in 1D optical lattices. She has also worked in LKB lab at the École Normale Supérieure at Paris in the lab of Professor Claude Cohen-Tannoudji, who is very world famous for his books on quantum mechanics. Later she worked in the laboratory Charles Fabry Institut d'Optique in France, and later in European Laboratory for Nonlinear Spectroscopy, which is in Florence, Italy. And she's currently working in the Light and Matter Physics group at the RRI. So today she'll be sharing her insights into the field and her expertise in the same. And the instructions to the audience is I request everybody to kindly switch off their mics till the end, and later the floor would be open for questions. Over to you, Sanjukta.
Thanks, Yash, for the nice introduction. So I start my presentation. So is it visible to everyone?
No, ma'am.
Yeah, it is.
Now, is my screen visible?
Yes, ma'am.
Yeah, it is actually visible. The ones who are facing problems may just try pinning
Yes, sir.
Sanjukta.
Yes, sir. Visible, sir.
It's visible, right? My slide is visible?
Yes, ma'am.
Okay. So I start. Today I'll be talking about actually the main theme of my research, which is quantum simulation with bosons and fermions and optical potentials. So I'm, as Yash had said in the introduction, so I have been working in few labs in India and in Europe, and now I'm also presently working at the Raman Research Institute. So this talk will be first, I'll give an introduction to ultracold atoms and Bose-Einstein condensate. Then I'll actually describe the experimental setup and methods for realization of BEC. Describe optical lattices, which are actually artificial crystals of light, and this enables quantum simulation with ultracold atoms and BEC in the optical lattice. An introduction to quantum simulation, and then I will show how quantum simulation of open problems in condensed matter physics can be done using quantum mixtures and optical potentials. And then I will show a few slides describing the quantum mixtures experiment at Raman Research Institute. No talk about Bose-Einstein condensation can begin without paying a tribute to the great scientists Satyendranath Bose and Albert Einstein. Satyendranath Bose had worked out the statistics for photons. So he was actually teaching in Dhaka University, and to answer a question from one of his students, he actually worked out the statistics, which is known as the Bose statistics for photons. And then he found the results quite interesting. And then he sent his results as a paper to Albert Einstein to get it published in a well-known German journal. And Albert Einstein immediately realized the importance of his work, and then he adapted the work by Satyendranath Bose to apply to bosonic particles and atoms, and thereafter he predicted the phenomena of Bose-Einstein condensation. So it was Bose-Einstein condensation is an exotic phenomena which was first realized in a strongly interacting system of superfluid helium in 1938. But it took 70 years to actually realize in a weakly interacting system of dilute atomic gases. So what is the prediction of condensation? The prediction states that the lowest energy state can be occupied by a large number of particles well above the absolute zero temperature. When the temperature is very low, very close to absolute zero, bosonic particles gather together at the lowest quantum state, even without any attractive interaction. And this phenomena is called Bose-Einstein condensation. And this is, in this phenomena, all the particles occupy the same quantum mechanical ground state and they are in phase. And that means we can say they are phase coherent. So let me explain Bose-Einstein condensation in simple terms. So when at a high temperature, the atoms behave like classical particles, like billiard balls. But as the temperature is reduced, as the temperature is reduced, the de Broglie wavelength of the particles, which is actually inversely proportional to the square root of temperature, that increases. So as the temperature decreases, the de Broglie wavelength increases. That means at lower and lower temperatures, the quantum nature of the particles are manifested more and more. Temperature, we have the de Broglie wavelength of the particles. They are overlapping together, and we get the phenomena of Bose-Einstein condensation. Very low temperature, very close to absolute zero, what we get is a pure Bose-Einstein condensate. So what is the requirement for a BEC? So this is what we experimentalists have to think about when we want to realize a Bose-Einstein condensate. So to realize a Bose-Einstein condensate, we need to have the phase space density, which is n multiplied by cube of the de Broglie wavelength, should be of the order of 1, or to be more precise, 2.612. Now n is the atom number density. And lambda, as I had explained, is the de Broglie wavelength, which you see is inversely proportional to the square root of temperature. Temperature is reduced to lower and lower temperatures, the de Broglie wavelength increases, and at the critical temperature for the BEC phase transition, they overlap and the particles go into the Bose-Einstein condensate phase. Now, at the BEC critical temperature, the typical de Broglie wavelength is around 300 nanometer. Now, the requirement for the BEC transition in terms of temperature and atom number density is like the typical temperatures for BEC phase transition is like 300 nanokelvin, and the atom number density is like 10 to the power 14 atoms per centimeter. Now, let's see where this temperature stands in the temperature scale. So as we know, liquid helium, which is already very, very cold, the liquid helium temperature is like 4 Kelvin. And then we go all the way to, and if we zoom there, we see that at near 0 Kelvin, we have the laser cooling, the temperature for ultra-cold atoms is like 100 microkelvin, and the BEC transition temperature is like 300 nanokelvin. Another advantage of going to very low temperature, as I'd explained, that the quantum nature of particles is manifested at ultra low temperatures, and this enables investigation or exploring the fundamental concepts of quantum theory. Well, I mean, if I would also, if you have any questions or need any clarifications, I mean, you can, without hesitation, ask me, because if I'm going too fast, you can always ask me for clarification.
Ma'am, there is one doubt regarding the
Yeah,
Bose-Einstein spinning of the
yeah,
photon.
yeah.
In our graduate level, we will teach there is the half spin particle or the full spin particle. What is the visualization of the photon? That is the full
So
spin.
yeah, it has integer spin. It has an integer spin particle. So all the particles which are like, for example, we work with rubidium, it has integer spin particle, and the particles which have like half integer spin, which are electrons, or so there are many other particles which are like half spin. For example, in elements also, you actually have bosons depending on what is the total number of the nucleons. Okay, so what is the total spin of the atom? So if the total spin of the atom is integer, you call it a bosonic particle, or if the total spin is half integer, call it a fermionic particle.
Here is right as the absolute temperature above the. Is it possible to acquire the absolute zero temperature in case of the boson?
No, it's not, because it's against the. I mean, it's it's a theorist can actually do the calculation using absolute zero temperature, but it's not in experimentally or in practically it's not possible. But we can go very close to absolute zero temperature, and the lowest one has gone it's in MIT. In the group of Wolfgang Ketterle, they have gone to around a few hundred picokelvins of temperature. So that's the lowest record temperature till now.
Okay, ma'am. Thank you.
The steps towards realizing a Bose-Einstein condensate is quite involved, and it involves several steps. So I won't go into too much details of each of the step, but I would like to highlight the main points. So what are the steps? So first and the foremost important step is laser cooling and magneto-optical trapping. So there you can actually lower the temperature from the room temperature to around 100 microkelvin temperature and get a atom number density of around 10 to the 11 atoms per centimeter cube. And still here, the phase space density is 10 to the power minus 6, way less than the phase space density required for the BC, which is like of the order of 1. So there are several steps, as you can see, to get the BC. So the first is the laser cooling and trapping, which actually cools the atoms from the room temperature all the way down to around Kelvin temperatures. So let me explain what it is. So as you can see that laser cooling reduces the temperature from around room temperature of 300 Kelvin to around 100 microkelvin temperature. Now, how does it happen? So generally, we think about lasers as heating up things. So how does it actually cool the atoms? So let's see, how do we manipulate the atomic motion using the radiation pressure from the laser beams? Suppose you have a laser beam which is moving towards in the opposite direction as the atom. So if the atom laser beam with a velocity v, and because of the Doppler shift, the atom actually sees the frequency of the laser upshifted. Now, if you see, this is the ground state and the excited state, and if the transition frequency is like omega, so if the laser is already red detuned, that means having a frequency less than that required for the atomic transition. So the atom will see the laser beam upshifted because upshifted because of the Doppler shift, and it will find it on resonance. And then the atom will absorb a photon and get a momentum kick opposite to its direction of motion. So as it gets a momentum kick opposite to its direction of motion.
Sorry, ma'am. Ma'am, please
Yeah.
one explain the absorption of the photon by the laser beam. Once again, repeat, please.
Yeah. So if you assume as a two-level system, it's having a ground state and excited state, right? Now we know that if the laser beam has a photon with an energy equal to the difference between the ground state and the excited state, then the photon will be absorbed by the atom. Right?
Yes, ma'am.
Yeah. So now we have to take care of the motion of the atom, because of which there is a Doppler shift. So there's a Doppler shift. So that's why we already have the frequency of the laser little bit less than the atomic transition frequency. Now, because of the Doppler shift, the atom sees the frequency of the laser beam upshifted and then thereby sees it on resonance and hence absorb a photon from the laser beam. And as soon as the atom absorbs the photon from the laser beam, it gets a momentum kick opposite to its direction of motion and hence gets slowed down. Now, as soon as it absorbs the photon, it also emits the photon using spontaneous emission. But that spontaneous emission happens in random direction. So, as you know, in 1 second, there are around 10 to the power 6 times the atoms absorb and re-emit the photon. So at each absorption, it gets slowed down. But for the spontaneous emission, it happens in random direction. So on an average, the effect of the spontaneous emission averages out to be 0. So what the effect remains is the slowing down of the atom at each of the absorption of the photon by the atom. See that there's a strong interplay between the dynamics of the internal and the external degrees of freedom, which leads to the cooling of atoms. So what happens now if you have laser beams shining on the atoms from both the direction? So you see whichever direction the atoms try to move, it gets slowed down. So as you can see in this figure, the force is actually having an opposite sign to the velocity. So that means the force of the laser beam is always opposing the motion of the atom. So towards the center at the low velocity class, you can see that the force is actually linearly proportional to the velocity. That means it's like a frictional force or a damping force, which is actually slowing down the atoms. So if you have the laser beams in all the 3 directions, the X, Y, and Z direction, what you form is a 3D optical molasses. So whichever direction in all the 3 dimensions the atom tries to move, it gets slowed down because of the Doppler cooling by the laser beams. Because the atom feels a viscous force within the laser beams. Now, here you can see a real picture of sodium atoms in an optical molasses. So you can see the cold atoms at the center, which are cooled down because of...
Ma'am,
Yes?
when the laser beam will strike to the photon, then the energy will be increases, no? Or decreases of the photon.
So that's what I have explained till now. That see in the earlier slide. So it is actually also following the conservation of energy. See, the atom is on at lower energy, but when it's doing spontaneous emission, it's actually emitting at higher energy. So this difference in energy is actually dissipated and taken away by the photon. Is it clear? So that is actually taken, this extra energy is taken away from the kinetic energy of the atom, and thus the atom is getting slowed down.
Yes, ma'am. Yes, ma'am.
So, but this is only damping force. So there's no trapping at a point in space. So how do we do the trapping? Trapping, we use something called a magneto-optical trapping. So for this, we use a spatially varying magnetic field, which is actually 0 at the center, and it's increasing linearly in all directions. Slide how we actually experimentally prepare it, but now I'm just explaining the concept. Now, when the magnetic field is 0 at the center and increasing linearly in all direction, so when the atom is at the center, which is like really where we want the atom to be, it doesn't experience any force. But as the atom goes away from the center, since the laser beam is already red detuned, that means having lower frequency than the transition frequency, it comes more on resonance due to Zeeman effect as the atom goes away from the center. So the more the atom goes away from the center, more the force it feels, which pushes the atom towards the center. So as it goes away from the center, it absorbs a sigma plus photon, and if it goes to the left side, it will absorb a sigma plus photon and get a force which will push it towards the center. And the same will happen in the other direction as well. So it's like a restoring spring force, which is actually pushing the atoms towards the center. So how do we actually realize it? We use a pair of magnetic coils in what is called a anti-Helmholtz configuration with the current flowing in opposite direction. So this is actually creating a 0 at the center, and it will create a gradient. So it will increase linearly in all direction, but give you the 0 at the center. So this is how we can trap and cool the atoms using magneto-optical trapping. So let us look at the typical parameters in a magneto-optical trap. The density is around 10 to the power 9 to 10 to the power 11 atoms per centimeter cube. The temperatures is around 100 microkelvin, and we can have size of the atomic cloud around even from starting from 100 micron to around 10 millimeter. Now here, one point to note is that still the interatomic separation is like around 10 to the power minus 5 meter, which is much, much larger than the atomic size. So that's why it's a weakly interacting dilute atomic vapor. Now, just to compare the velocity, the typical velocity of room temperature atoms is like 30,000 centimeter per second. Now, compared to that, a typical velocity of atoms in a magneto-optical trap is like 10 centimeters per second. So they are really cold and at very low temperatures. So how do we actually realize that? Now, just to start with our experiment in TIFR, where we had actually realized the first BC, we had to adopt a very specialized strategy to have as much number of atoms in our trap, because as I will show in next after a few slides, that the actual process of getting to the BC, it involves something called evaporative cooling, which includes loss of atoms. So we wanted really to start with a very large number of atoms to start with. So we had designed a special trap called a two-dimensional magneto-optical trap, which is actually called a 2D plus magneto-optical trap, which is trapping in 2 dimension in the transverse direction, but cooling only cooling in the 3rd direction. So you can see there are rectangular magnetic coils, which is creating not a point of 0 magnetic field, but a line of 0 magnetic field at the center of the rectangular vacuum chamber. Now, one point I forgot to mention, that these atoms are actually kept in a vacuum chamber with a very ultra high vacuum. So if you can compare the vacuum, so you have the atmospheric pressure like around 760 torr, and we need the vacuum inside the vacuum chamber to be around 10 to the power minus 11 torr. So it's like really 10 to the power 12 orders of magnitude lower at pressure as compared to the atmospheric pressure. This is because we don't want the hot atoms to actually knock out the very, very cold atoms in the magneto-optical trap, which are very low energy. So here we devised an experiment to actually realize a cold atomic beam to load the 3D magneto-optical trap. So this is how we did two-dimensional trapping in the transverse direction and only cooling in the third direction. And then we actually we passed the cold atomic beam through a cylinder with a very, very narrow hole, and then this cold atomic beam could pass all the way through the tube to load a 3D magneto-optical trap. So this is a picture of the cold atomic beam, which we realized, and then it was a very successful experiment, and this actually was one of the initial main reason we could realize the Bose-Einstein condensate with a good atom number. So here we have produced the cold atomic beam, which loaded a 3D magneto-optical trap, and we could get a cold atomic beam with very high flux of 10 to the power 10 atoms per second, and we could get a very, very large magneto-optical trap with 10 to the power 10 atoms. So this experiment, this design for a 2D plus Mott was actually followed in many other labs in the world who wanted to realize an experiment for BEC, starting with a very large number of atoms. So this is actually the photograph of our experimental setup. So on the right, you see the vacuum chamber for the 2D plus magneto-optical trap, and then on the left you see the bigger cylindrical vacuum chamber where actually the 3D magneto-optical trap was produced. So we had a very large number of atoms in the magneto-optical trap. So it was emitting a lot of fluorescence that we could actually see the atomic cloud with directly without using a CCD camera. So here you can see this red rubidium Mott directly, which was taken using a digital camera, a normal digital camera. So you must be wondering, how do we say that, okay, this is the temperature of the cold atoms? We actually cannot place a thermometer inside the vacuum chamber, but we have our special methods to do the temperature measurement. So what we do is we release the trap. We switch off the magneto-optical trap and let the atoms fall and expand. Now, the higher the temperature of the atoms, so the higher will be the momentum of the atoms and the faster it will expand. We probe the expansion of the atoms using a probe light and have the probe light on the detector, and from the width of this atomic density profile, or how much it has expanded in a particular period of time, from the width we can actually know what is the temperature of the atoms. So how do we actually see the atoms? We see the atoms by using absorption imaging. So we pass a probe beam, which is resonant to the atomic transition, through the atoms, and then we image the shadow of the atoms in the probe beam on a CCD camera. So that's how you can see that this dark part you can see is actually the shadow of the atomic cloud imaged on a CCD camera. So that's how we detect the atomic cloud, and from this absorption image we can extract all the necessary information we need for the atomic cloud. We can know the number of atoms, we know the temperature, we can know of course the size of the atomic cloud. So for laser cooling and trapping, which I had described till now, the three great physicists, Stephen Chu, Claude Cohen-Tannoudji, and William D. Phillips, they got the Nobel Prize in 1997 to develop methods to cool and trap atoms with laser light. So now, as we saw that the lowest temperature we can get by laser cooling is like around 40 microkelvin. Now, how to cool even lower to go to BC phase transition? So we need around few hundred nanokelvin to go to BC phase transition. So how do we cool further? Now, you may ask, okay, we laser cool further and go there, but it's not possible because of something, a limitation called the single photon recoil limit. Now, as I said, that these photons which are used to cool down the atoms, they are on resonance. But these are also, because of spontaneous emission, they also cause a little bit of heating of the atoms. So the heating by a single photon absorbed by the atom is like around 1 microkelvin, of the order of 1 microkelvin. So we cannot actually go below 1 microkelvin, because if we are having resonant photons to cool, we cannot go below that temperature. So we need something where we don't have any absorption of any resonant photons. So we need something called dark traps. So there are two kinds of dark traps, which is like absence of resonant light. So we have two kinds of dark traps where we do the next step for going to the BC, which is the evaporative cooling. So the options are magnetic trap. Option is the optical dipole trap. Now, so this is what we had adopted for going to the BC at TIFR. So what is an optical dipole trap? So if you have a very high power laser, whose frequency is very far away from the atomic transition, so that there's no absorption of the photon to heat up the atoms. If you focus the laser beam at the point where you have the atomic cloud, it actually creates a potential for the atoms to be trapped. So the potential, the depth of the potential is proportional to the intensity. That means higher the intensity, which is the largest at the focal point, the higher the intensity, more is the potential depth, and the more number of atoms you can trap, and larger is the detuning. That means you can see that the detuning, which is the delta, is in the denominator. So the larger the detuning, so lower will be the scattering rate. That means lower will be the heating. So we use very high power lasers with very high intensity and very far away detune from the atomic transition to get a optical dipole trap. Now how, so here you can see a picture of a crossed optical dipole trap where we have loaded atoms from the magneto-optical trap. So you can see that atoms which are trapped in the optical dipole trap, they are actually, you can see the crossed image of the atoms in the cross dipole trap, and the atoms which are not be trapped in the dipole trap, they are, they are getting lost as we switch off the magneto-optical trap. Another way actually to trap the atoms in a dark trap, which is using a magnetic trap. So we use a quadrupole magnetic field with currents in, we have two coils in anti-Helmholtz configuration with currents in the opposite direction. So which creates a zero at the center and it increases linearly in all directions. So that creates a magnetic trap where you can actually trap the atoms. Now, the very important step to go to the Bose-Einstein condensate is something called evaporative cooling. So how do we do that? So once the atoms are trapped in one of the traps, so what we do is we lower the depth of the trap. So here, when the atoms are actually trapped in a harmonic trap, the higher energy atoms are actually at the outer region of the trap, and the lower energy atoms are actually at the center of the trap. So when we lower the depth of the trap, the hotter atoms, which are at the periphery of the trap, they get lost and get evaporated away from the trap. And the lower energy atoms, they actually elastically collide among themselves, and then they overall, and then they lower the overall temperature and get cooled step by step. So this is like actually cooling off your coffee cup, where the hot atoms are getting evaporated from the cup, and the lower energy atoms are actually colliding, and then it's reducing the overall temperature of the system. So after you lower the atoms step by step, you go to a very low temperature and actually cross the BEC transition temperature to get all the atoms at the lowest momentum state of the trap, and thereby reach the BEC phase transition. So how do we know that we have a BEC? So we need to have some smoking gun evidence or the signatures of a BEC. So one very good harmonically trapped BEC is that the Bose-Einstein condensation occurs in both position and momentum space. That means the higher momentum atoms are really at the periphery, and the lower momentum atoms, or the coldest atoms, are at the center of the trap. So how do we realize that the BEC transition temperature has been reached? So it is observed as a sharp peak in the atomic density profile, which emerges at the center of the trap, which results in a bimodal profile. So you will have a periphery of atoms which are not in the condensate. We call them thermal atoms, and we have the Bose-Einstein condensate at the center. The atomic density profile from our from the BEC in which we had realized at TFR. So here you can see that there is a broad profile of the thermal atoms, and there you have a sharp peak which corresponds to the dense atomic cloud at the center, which is the Bose-Einstein condensate. So the coexistence of condensate and the thermal cloud is a characteristic of BEC in a harmonic trap, and also the smoking gun evidence. See that when you have not reached temperature, where you have high temperature, there you have only thermal atoms. But when you have reached the BEC transition temperature, you have a coexistence of the thermal cloud and the Bose-Einstein condensate, which is a sharp peak at the center. And as you lower the temperature further, you have only the Bose-Einstein condensate. So how to explain this parabolic profile, which is the characteristic of the Bose-Einstein condensate? So this has to do with the interaction of atoms in the Bose-Einstein condensate. Now, how do we explain the atoms in a Bose-Einstein condensate in a harmonic trap? Explain it using a Gauss-Pittelewski equation, which is actually a nonlinear Schrodinger equation. So it is actually consists of a kinetic energy term, the term for the external potential, and we have an interaction term. Mean field interaction. Now, in the Thomas Fermi limit, we have a limit where the kinetic energy is 0 because the atoms are very, very cold. We have the atomic density profile, which is actually gives the shape of a parabola. So that actually explains why you have a parabolic shape, which is the signature of the Bose-Einstein condensate. So here you have a video where actually the density profile is shown at various stage of the BEC. So here you can see a sharp density peak appearing at the center, which is actually the smoking gun evidence of the Bose-Einstein condensate. So for realizing the first Bose-Einstein condensate in the world, so it was realized in Zila in rubidium by Eric Connell and Carl Weimann, and in MIT by Wolfgang Ketterle, and they won the Nobel Prize in 2001 for achieving the Bose-Einstein condensate in dilute gas of alkali atoms for the first time. So this is actually the cover page of the journal Science, where the first report of the BEC was, so here you can see that the BEC was actually compared with soldiers marching in locksteps. So it's like atoms marching in locksteps because they are all phase coherent. Picture of a BEC in our TFR experiment, where we have before the transition temperature, like at around 700 nanokelvin, we have fully thermal atoms, and then we cross the BEC phase transition, and we see a coexistence of BEC and the thermal cloud, and then we have a pure Bose-Einstein condensate as we go to lower temperature. Have a 3D profile of the Bose-Einstein condensate, and here the BEC phase transition is shown nicely in this graph, where you see that before the transition temperature is reached, the condensate fraction is 0, but at the BEC phase transition, that we see a sudden jump in the fraction of atoms in the Bose-Einstein condensate. BEC team comprised of me and another PhD student, Saptarishi Chaudhary, and we worked under guidance of our supervisor, C.S. Unnikrishnan. So this is the picture of our BEC experimental setup. So here we have the place where we actually realize the BEC, and all the optics are actually to have the laser beams just at the correct amount, correct polarization and intensity to actually realize the Bose-Einstein condensate. Well, I mean, it looks a bit complex, but when you actually see the nice image of Bose-Einstein condensate on the CCD camera, you think that it's totally worth it. So as I said, that Bose-Einstein condensate is a coherent matter wave, and the smoking gun evidence for a coherent matter wave is that it should be able to create interference pattern. So this is a picture of atom interferometry, BEC atom interferometry in MIT, where the condensate was split into two and then made to recombine to get an interference pattern, which was actually evidence that all the atoms in the Bose-Einstein condensate are actually phase coherent. So also an interesting property of BEC is its superfluidity. So if you actually rotate the BEC, you can actually see vortices. So the faster you rotate, you will see more and more vortices appear in the BEC, which has a form of something called an abrasive lattice, similar to what you have in a superconductor. So next, I explain a new setup for BEC, which I realized during my postdoc in Florence. So it is with a potassium. So till now I showed you a BEC of rubidium. So in Florence, I actually built up a setup for potassium BEC, and it has a very nice advantage, which I'll show you in a few slides. So we, as I said, our 2D plus mod design in many experiments in the world, and this experiment was also one of them, which I had set up from the beginning. So this had a 2D plus Mott and a 3D pot, and then we actually magnetically transported the atoms from the 3D Mott to a chamber where we did all the science experiments. So potassium had a very nice property that you could actually change the interaction between the atoms using something called a Feshbach resonance. So we changed the magnetic field, and using what is called a Feshbach resonance, we could change the scattering length or the interaction of the atoms from minus infinity to plus infinity. So it was a very nice control knob for changing the interaction in the potassium atoms. A very large variety of Feshbach resonance by which we could control the interaction. So here is the experimental setup for our potassium experiment. And here you can see the video where after producing the atoms in a 3D bond, we would transport it magnetically into the science cell. So here we is a picture of the BEC phase transition in potassium. So this was actually the first single species BEC for potassium, because in earlier experiments, since potassium didn't have a very favorable scattering length for evaporative cooling, it had to be mixed with rubidium to get the BEC. But here we have used Feshbach resonance to tune the interaction to a favorable quantity in the potassium to realize the BEC. So it was for the first time we had a single species potassium 39 BEC. So it was a very large BEC with around 10 to the power 6 atoms. So here is the effect of the interaction. So you can have either attractive interaction or repulsive interaction in the BEC. So when you have repulsive interaction, which we actually need for evaporative cooling to BEC, you can see that as we are increasing the interaction, which is actually equivalent to increasing the scattering length of the atoms, you can see that the BEC, they're all in BEC, they are getting larger and larger because of the repulsive interaction between the atoms in the BEC. So we also did atom interferometry with Bose-Einstein condensate. So BEC is a very useful atomic tool to do very precise atom interferometry. And it can actually lead to quantum enhanced measurement, like beating the standard quantum limit, and also can realize entanglement between atoms, and it can eventually reach the Heisenberg limited resolution. So it's a very high sensitive sensor with very high spatial resolution. So to get the atom interferometry, we first produce a BEC in a double well trap, and then increased the spacing between, we separated the BEC, and then we introduced a phase shift, and then again recombined the BEC to get the interference. So here we have the BEC in a single trap, and then we actually split the BEC into two, and then let it expand and recombine to get the interference pattern. So here you can see the real interference pattern of the BEC after we split it and recombined. So it's a very useful tool for high precision atom interferometry. So next I move over to optical lattices. So optical lattices are actually artificial crystals of light, and quantum gases in optical lattices can actually emulate or can be thought of as analogous to electrons in solid state lattice. So how do we make an optical lattice? We can have a 1D optical lattice by just retroreflecting a laser beam. So it forms a standing wave, and atoms can be actually trapped in the antinodes of the standing wave. Now, if you have a 1D lattice, so what we get in each of the site of the optical lattice is a sort of pancake-shaped atomic cloud, which are in a 2D geometry. Now, if you have 2D optical lattice, that means you have optical lattice in X and Y direction, you get an array of 1D or rod-shaped atomic cloud, and you can have also a 3D optical lattice. So here you can see that you can actually control very well the geometry of the atomic cloud using the optical lattice. So you can go to 1D, 2D, and 3 dimensions and explore a wide variety of physics by using Bose-Einstein condensate in what is called an optical lattice. So you can actually control the geometry of the beams to make realize a variety of optical lattice, like a checkerboard, triangular, dimer, honeycomb lattice, which are very important to realize graphene physics. So next I come to quantum simulation. So what is a quantum simulator? So according to the words of one of the greatest physicists, Richard Feynman, Quantum simulator is one controllable quantum system simulating another quantum system. So you can have two kinds of quantum simulator. One is a digital quantum simulator, which is actually the universal quantum computer, which is yet to be completely realized. But we can have another kind of quantum simulator, which is the analog quantum simulator, and we have the technology for analog quantum simulator completely within our reach. And that is what my main theme of the experiments which I'm going to describe now. Now, for the analog quantum simulator, we need a quantum system which has to be mapped to the Hamiltonian of the simulated quantum system. Now, it should have a sufficient degree of similarity between the system which we are simulating and the quantum simulator. So we can use Bosons and Fermions to do the quantum simulation, or we can use, as we are going to do in our experiment at RRI, a mixture of boson and fermions. So why it's so much advantageous to do quantum simulation with ultra-cold quantum gases in optical lattice? As you may have realized, we have so many controllable parameters. We can control the dimensionality, we can control the lattice geometry, we can control the tunneling between the lattice sites, we can control the interactions, and we can control the external potentials. So we can actually control the system parameters in the same way as we do numerical simulation in a computer, but it's actually done in a real system with atoms. So it also enables to reach parameter range, which may be not even achieved in the real system. So you can have possibility to explore new physics by doing this quantum simulation. So there are a lot of variety of quantum simulation which has been done with quantum gases in optical lattices. We have superfluid to Mott-insulator transition. We have something called a BEC to BCS crossover, which has been done using fermionic atoms. We have, in other groups, there have been simulation of graphene physics, using BEC in honeycomb lattice. There have been also simulation of two-dimensional physics like BKT transition, and of course there is Anderson localization, which I'll be talking about in a few slides, and also quantized vortices, which I have shown a few slides ago. So there is a wide variety of physics which you can do using quantum gases in optical lattices. So one of the very important phenomena, which was and one of the first results which actually with quantum gases is superfluid to Mott-insulator transition, which was actually realized in MPQ Munich, where the quantum gases in optical lattices, where when you have the tunneling energy much higher than the interaction energy, the BC was like a superfluid in the optical lattice, and when the interaction energy was dominating, what you Mott-insulator. So this is a pure condensed matter phenomena which was realized in a very well-controlled, clean system with quantum gases in optical lattice. So next I'll talk a little bit about quantum simulation with BEC in disordered potential, which I had done during my postdoc in Florence. So as we know that conductivity is one of the main areas of study in condensed matter physics. So study of the conductance of electron in response to an external electromagnetic field is actually at the heart of condensed matter physics. Now, for the from the classical model for metals, it was believed that disorder or randomness in a solid state lattice, it actually hinders ohmic conduction, but it cannot cancel it. And so classical particles which were scattered on the lattice defects were actually giving rise to diffusive transport. But there was a paradigm shifting paper by Anderson, who in 1958 said that disorder or randomness in a solid state lattice can completely cancel the conduction. So he predicted a metal insulator transition due to interference of multiple scattering paths, which led to localized wave functions with the characteristic exponentially decaying profile. So if you have an ordered lattice, which is on the left, you have an extended wave function. But when you have a disordered lattice side due to destructive interference of the scattered waves, scattered matter waves, you get a localized wave function with exponentially decaying profile. So one condition which has to be satisfied to have the Anderson localization, which is called a Eye-of-Rigel criteria, which is that the mean free path should be less than the de Broglie wavelength. So the destructive interference of the rescattered matter waves from the multiple scattered in a disordered lattice actually leads to exponentially decreasing wave amplitude, which actually leads to Anderson localization. So what I did in Florence is a 3D Anderson localization. So the 3D Anderson localization is actually characterized by a critical energy called the mobility edge, which actually marks the transition from a diffusive state to a localized state when you increase the amount of the amplitude of the disordered potential. So this critical energy was not precisely measured before, but we needed it very, this mobility edge, precise measurement of mobility edge was very much needed to actually resolve a lot of open problems in disordered physics. So we actually loaded the BEC or the quantum gases in a disordered optical potential. So how do we make that disordered potential is actually passing the laser beam through a diffusive glass plate and actually forming a random potential at the place where the atoms were trapped. So atoms were actually loaded in a disordered optical potential. And hence, by controlling the appropriate parameters, we could realize a 3D Anderson localization with the characteristic exponential decaying profiles, as you can see in the figure. So here we could have a very precise measurement of the mobility edge, which actually marks the phase transition to the Anderson localized phase. So this is one of the very important quantum simulation of disordered condensed matter physics, which we have done using ultra-cold atoms in disordered optical potentials. So this was our group in Florence, Italy, who have together done this work. Now here it's the last part of my talk where I actually talk about quantum simulation with Bose-Fermi mixture in optical lattices, which we are pursuing presently at Raman Research Institute. So why Bose-Fermi mixture is important? Because it's everywhere in nature, you have interaction of fermions mediated by bosons. For example, in standard model, you have the interaction between the fermionic particles. They are mediated by gauge bosons. You have the quarks, which are fermions. Between them, the interaction is mediated by gluons, which are bosons. Also, you have the electrons dressed by the lattice vibrations of the ions, which forms polarons. And also, we have the interaction between the electrons in a Cooper pair is mediated by phonons. So you see that how everywhere in nature you have bosonic bosons mediating the interaction between the fermionic particles. So we have a few ideas where we would like to quantum simulate condensed matter physics, where there are open problems using Bose-Fermi mixture in optical lattice and disordered potential. For example, we all know that the rigorous theory for unconventional superconductivity or high temperature superconductivity is still an open problem. But here, we can actually use Bose-Fermi mixture in a 2D optical lattice to simulate unconventional superfluidity or high temperature superconductivity and explore the parameters which can give us understanding about the basic physics of high temperature superconductors. So it has been predicted that if we have Bose-Fermi mixture or a mixture of sodium and potassium, which is our experiment at RRI at present, if we have the potassium as the fermionic species and sodium as the bosonic species, the sodium being the bosonic species can actually mediate the interaction between the fermions and actually can simulate the physics of unconventional or high temperature superconductors, and which is actually given by the signatures like charge density wave or D wave or P wave superfluidity, which are the signatures of high temperature superconductors. Also, we can have Bose-Fermi mixture in disordered potential, where we can have one species actually trapped in the disordered potential, and that giving rise to scattering of the other species. So this is actually will be enough, Anderson localization, where one atomic species is actually causing a disordered potential for the other atomic species. So these kind of open problems have not yet been addressed in condensed matter physics as well as in ultra-cold atom physics. Also, we have something interesting in mind to explore with Bose-Fermi mixture, is something called a spin glass, where we have a spin in disordered potential with random interaction. So if you have spins in triangular as well as in a disordered potential, you have something called a random coupling and a frustration. So if you have in a triangular lattice, so if you have spins with if you want to have opposite spins in each of the sides of the triangular lattice, so it creates some kind of frustration because it has so the spin doesn't know which way to point, and this leads to frustration, and this is actually the basis of spin glasses. So we are going to use Bose-Fermi mixture in disordered triangular optical lattice to address this open problem of spin glasses. So now I show the quantum mixture experiment at Raman Research Institute. So here we are actually building up an experiment of sodium and potassium, where potassium will be the fermionic species and sodium will be the bosonic species. So we have an experiment where we have two-dimensional 2D plus magneto-optical trap for sodium and potassium, which will actually load a single 3D bot, which will give a mixture of sodium and potassium in the magneto-optical trap. And then we will have a magnetic transport, which will load the mixture of cold atoms in a signed cell, where we have a quantum degenerate mixture of sodium and fermionic potassium. So this is actually the design of the vacuum assembly, the design of the magnetic transport. So we already have the vacuum assembly in place, and we are very soon going to have both the sodium and atomic quantum mixture species in our experiment. And here is our potassium. The sodium atomic transition is in the visible region of 582 nanometers. And so here we are looking forward to a wide variety of exciting physics, which I have described just now, with the mixture of sodium and potassium quantum gases. So this is the quantum mixture team in Raman Research Institute. So with this, I come to the end of my talk. So to summarize, I've given an introduction to ultra-cold atoms and Bose-Einstein condensate. Then I've described how quantum gases and optical potentials can be used as quantum simulators for condensed matter physics. And then I have described a few ideas to do quantum simulation of using Bose-Fermi mixture in optical potentials. Thanks for your kind attention.
Yeah, thank you, Sanjukta. That was a great talk and a very, very informative talk. Thank you for the talk. We have a few questions from our audience.